Diodes are devices with two terminals. One terminal is called anode and another terminal cathode. Diodes exhibit direction dependent properties. They allow current to flow from anode to cathode, but they prevent current flow from cathode to anode. Diode comes into being when two slabs of a semiconductor, one p-type and another n-type. These two slabs are brought together. Outwardly, it appears there is one p-type slab on one side and one n-type slab on the other side, but at the interface of these two slabs, there comes into being another region 2, that is junction region. Diode length is usually less than half centimeter, and the width of the junction region is less than half micron. Junction region characteristics are totally different from the characteristics of P region or N region. In P region, plenty of holes exist. In N region, plenty of electrons exist. Therefore, in P region as well as in N region, plenty of current carriers exist. Therefore, conductivity of these two regions is very high. In junction region, you can find no free electrons or no holes. So there exists no mobile current carriers in junction region. Hence, conductivity of the junction region is almost nil, zero. P region or N region, it comes into being when impurities are added to an intrinsic semiconductor. This addition can be in different types. In some slabs, addition is uniform all along its length. When in the diode formation, P slab and N slab, they have their impurity addition uniformly all along their lengths, then the resultant junction, the resultant diode is called step graded junction or step graded diode. In some cases, in some slabs, what happens is impurity addition increases from one end to another end in a linear manner. When slabs with impurities increasing linearly from one end to another end, those slabs are used for the formation of the diodes, for the formation of the junction. Then the resultant resultant diode is called linearly graded junction. Apart from these two types of junctions, other types of junctions are also possible. For example, on one side, impurity addition may be uniform, on the other side, it may be linearly increasing. Electronic Devices Junction Diodes Part 1 Series on Semiconductor Devices and Circuits Lecture number 2.11. Diodes are two-terminal devices. One terminal is called anode, another terminal is called cathode. These are unilateral devices. It means when current tries to flow in one direction through the device, they offer small resistance, but when the same current tries to flow in the opposite direction, they offer very high resistance. Mostly they are passive, but there are applications. There are uses where the diodes act as active element. They have several applications. Most common application is in rectification. Other applications include clipping, clamping, etc. With this small introduction, now let us move to the core session where we try to understand the functioning of diodes, semiconductor diodes, PN junction diodes. Let us start the session with certain general points or common points pertaining to junction diode. Now it requires to be mentioned that a diode can be made with vacuum tube technology or with semiconductors. In the beginning of the electronic revolution, tube technology, vacuum tube technology, it was used to construct diodes, triodes, etc. But after the advent of semiconductor technology, diodes mostly they are made with the semiconductor technology and they are called semiconductor diodes or PN junction diodes. Now, diodes which require to operate at a very high voltages, very high power levels, they only use vacuum tube technology for their fabrication. All other diodes use semiconductor technology. So mostly at present 99% of the diodes are semiconductor diodes. Our discussion, our focus in the present session is on semiconductor diodes, junction diodes. Some general points are given in this slide. As a beginning, it is a two-terminal semiconductor device. It is passive or active depending upon the use. Certain diodes, they are used as active element in amplifier circuits like tunnel diode or varactor diode. In such cases, the diode is acting as active device, but it is very rare. Most of the times, the diodes are used as passive devices like in rectifier circuits or clipper circuits or clamping circuit. Diodes are unilateral and these are also nonlinear devices. Ideal diode exhibits zero or infinite resistance, but in practical diodes, it is small, not zero. It is or large, not infinite. The point is ideal diode, practical diode. Ideal diode is one which is a short circuit in one direction and open circuit in other direction, the direction being direction of current flow. So it can act as a short circuit, it can act as an open circuit. That is the case of ideal diode, but in practice, it is not a short circuit, it is not open circuit. It is simply small resistance. It is simply large resistance, not zero or infinite resistances. Structurally, diodes consist of a P region, an N region, and a junction region. Three regions exist. It is like this. One side P-type semiconductor, other side N-type semiconductor. In between, there exists small region. This region is called a junction region. So diode means structurally three regions with different properties. P and N regions are field free, whereas junction region carries field always. In this region, there is no field. In this region, also no field. But here, in the junction region, there exists always field. It is mainly diffusion phenomena in P and N regions, and it is drift phenomena in junction region. What is diffusion phenomena? Carriers, current carriers, like electrons, holes, if they move due to the existence of concentration gradient, then that process is called diffusion process. Diffusion. Notice it leads to existence of certain amount of current. So diffusion leads to current. This process exists in P and N regions. Whereas drift process, what is drift? Movement of carriers can be due to the existence of potential gradient under the influence of electric field. This process, this way of movement of current carriers under the influence of field, it is called drift. Diffusion and drift, these two are processes that exist in the functioning of PN junction diodes. You are going to see out of these two, however, diffusion is going to be the major process in the functioning of, in the working of PN junction diodes are in general semiconductor devices. Another set of points. There exists a voltage across junction region. It is called built-in potential. Symbol is V0. Regarding dimensions of diode, its length is approximately 0.5 cm, half cm, and the junction width is approximately 0.5 micrometers. This is diode. It is half cm, 0.5 cm. In the middle, there exists junction region. Its width is 0.5 micrometers. The impurity concentration is usually 1 part in 10 power 8 or 10 power 14 atoms per cm cube. 1 part in 10 power 8. This is one way of mentioning impurity concentration. Another way is 10 power 14 impurity atoms per cm cube. This is another way of mentioning impurity concentration. Both mean same. 1 part in 10 power 8 is same as 10 power 14 impurity atoms per cm cube. In case of step graded junction, doping is uniform, and in case of linear graded junction, impurity concentration changes in a linear manner. What is step graded junction? This is diode, this is junction. Let us suppose this is P region, this is N region. If impurity concentration is uniform on P side, uniform on N side, then it is called step graded junction. If impurity concentration changes in a linear manner, like this, N side linearly increasing, this side also linearly increasing, P side too, then it is called linear graded junction. Diodes exhibit capacitance. There are two components in the capacitance. One component is transition capacitance and the other one is diffusion capacitance. We are going to talk about these capacitances at length very soon. Several types of diodes are there. Broadly, diodes can be divided. Semiconductor diodes can be divided into two categories: ordinary diodes, special diodes. What are ordinary diodes? Diodes that are used for the purpose of rectification, clipping, clamping, etc. Then they are called ordinary diodes. Special diodes are diodes which are used for purposes other than common usages like clipping, clamping, and rectification. Example for special diodes are varactor diodes, Zener diodes, tunnel diodes, LEDs, photodiodes, etc. Here a brief is given on ordinary and special types of PN junction diodes. Ordinary diode, this is general purpose diode. Symbol is shown here, one arrow with an obstruction symbol. These are used for rectification, clipping, and clamping. Varactor diode, this falls in the category of special diodes. It is well known for voltage variable capacitance. Symbol is shown here. Ordinary diode symbol modified by adding variable capacitance symbol. Varactor diodes are used as tuning capacitors and in parametric amplifiers. Zener diode, this is another special diode. It is used for regulation purpose, voltage regulation purpose. Fixed voltage operation is the result when we use Zener diode as regulator. Symbol is shown, ordinary diode modified by adding Z, used for regulation and protection. Another special diode is tunnel diode. It is well known for its negative resistance. It is used in the design of low noise microwave amplifiers and microwave oscillators too. Tunnel diode, when it is used in amplifiers, in oscillators, it acts as an active device. Another special diode is LED. LED stands for light emitting diode. Its specialty is it emits light, used as a transmitter in fiber optic communications. LEDs, they have plenty of applications. You see the symbol of LED? Ordinary diode with two arrows indicating light moving out. Another category of special diodes is photodiodes. These diodes, they are able to detect the presence of light or absence of light, senses light, used in receivers of fiber optic communications. This is a small introduction kind of thing for diodes and varieties of diodes. Now, let us move slightly deep into diodes. Diode is a single crystal with the donor impurities introduced into one side forming N region and acceptor impurities into other side forming P region. It is a single crystal. It may be silicon crystal, it may be germanium crystal, it may be gallium arsenide crystal, or it may be some other crystal, but it is a single crystal. N-type impurities added on one side, P-type impurities on the other side. Then diode comes into being. Let us suppose interface between P and N regions is a straight line like this. This is interface. One side P, another side N. After addition, immediately what happens is a small region surrounding the interface. This region, it is a special region. It is different from P region. It is different from N region. It is called junction region or depletion region. This region comes into being. How it comes into being, why it comes into being, it is not difficult to understand. Left side of the interface, P region, right side it is N region. So left side plenty of holes, right side plenty of electrons. Holes are positively charged, electrons are negatively charged, and both holes and electrons are mobile, and attraction is there due to Coulomb's force. So what happens is they combine. holes from p side, electrons from n side, they join, they combine with each other, resulting in disappearance of both holes and electrons. The region where holes and electrons completely disappear, that region is junction region. Further discussion on the formation of junction region. It is done very soon in this session. Both P and N regions are with a lot of carrier concentration, giving a very high conductivity. Hence, field cannot exist in them. Here the point is this: consider point form of Ohm's law, J equal to sigma E. From this, E equal to J by sigma. P and N regions are with a lot of carrier concentration, therefore sigma in either region, sigma is very huge. When sigma is very huge, what happens to E? It becomes negligibly small, or it is zero. Hence, a field cannot exist either in P region or in N region. In the area where these two regions merge into each other, another distinct region comes into being. It is called depletion region. As already mentioned, this is depletion region. Another name for depletion region is junction region. It is also called transition region. Hence, after formation, the diode possesses three distinct regions, which was already mentioned. In P or N region, there exists high concentration of holes or free electrons. In P region, holes; in N region, electrons. The free electron or hole concentration is very small, even less than the intrinsic carrier concentration Ni. So the point is this: in P region, plenty of holes exist. In P region, apart from holes, there exist free electrons also. So in P region, the free electron concentration, it is non-zero, but it is very small, but it is not zero. In N region, plenty of electrons exist, but there holes also exist. Hole concentration in N region, it is not zero, but it is very small. It is said that it is even less than intrinsic carrier concentration Ni. A metal wire called anode or cathode, it is connected to P or N region to provide electrical contact with the outside circuit. Till now we are talking about semiconductor part of diode, P region, N region, junction region. Okay. What he says is a metal wire is connected to P side. This wire is called anode. Another metal wire is connected to N side. It is called cathode. Through anode and cathode, we can connect signal. We can connect bias to the diode. When the impurity concentration is Na, impurity concentration is Nd. Na refers to impurity concentration on P side, Nd refers to impurity concentration on N side. Then the carrier concentrations are PP naught. PP naught means whole concentration on P side under thermal equilibrium condition. It is equal to Na. N naught means electron concentration on N side under the thermal equilibrium condition. It is Nd. Np naught means electron concentration on P side under thermal equilibrium condition. It becomes equal to approximately Ni square by Na. Ni means intrinsic carrier concentration. Pn naught is approximately equal to Ni square by Nd. These relations, they are derived using mass action law. Now, a few points regarding the formation of junction region diode. Here is a piece of semiconductor from here to here. On one side, p-type impurities are added, another side n-type impurities are added. These impurities goes inside, displaces some of the semiconductor atoms, ultimately resulting in good number of holes on p side, good number of electrons on n side. You can see the interface between these two regions. It is indicated by a discontinuous line, this one. Now, around the interface, one side there are holes and negative ions. Hole, 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 negative ions. On the other side, positive ions and electrons. This side, electron. Holes and electrons, they are mobile, they are free, and as they are oppositely charged, there exists attraction between them. So these electrons and holes, they move towards each other, meet each other, resulting in their recombination. As a result of recombination or neutralization, both electron and hole both disappear. So now here you don't have hole, you don't have electron, no hole, no electron, no hole, no electron, no hole, no electron. But notice, due to the disappearance of hole and electrons from the ions, what we have right now is a column of negative ions on p side, a column of positive ions on n side. These two columns can be viewed as a parallel plate capacitor. Right plate with the positive charge, left plate with the negative charge. Between the plates, there exists a field. That field is from positive plate to negative plate. So the point here is, after neutralization, certain field comes into being. The direction of the field is from N to P side. Most important point to note here is that the direction of the field that has come into being, it prevents, it doesn't allow the movement of holes from P side to N side, electrons from N side to P side. So holes remain confined to p-type region, electrons remain confined to n region. Only first column electrons or holes, or second column, or at the most third column. Only these electrons, holes, there is a chance for recombination. Other columns of electrons and holes, they cannot move because their energies are not sufficient to overcome the opposing force that is exerted by the field that exists across the junction region. This explains how junction region comes into being. In this diagram is also shown the dimensions. It is 0.5 cm. The entire diode length is 0.5 cm. Another aspect one has to keep in mind is, field is there across the junction region. Wherever field is there, potential also exists across the junction region. So this potential is called built-in potential. Now some more information regarding formation. Junction region is also known as depletion region, space charge region, transition region. It exists as a layer surrounding the interface between P and N regions. On one side of the interface, there exists ions of P-type impurities and holes, and on the other side, ions of N-type impurities and free electrons. The free electrons on one side travel to the other side and recombine with the holes, thereby neutralizing each other and leaving behind a row of negatively charged p-type ions on one side and n-type ions on the other side, forming the junction region. Some more points. The ions of opposite polarities facing each other establish electric field from positive ions to negative ions, thus preventing further movement of electrons from N to P side and holes from P to N side. A voltage called built-in potential comes into being across the junction region, as the fields are always associated with the potential. The N side remains at a higher potential level when compared to other side. The depletion region, junction region, transition region, these are all different names to one area. It is characterized by the absence of mobile charge carriers and with the presence of immobile impurity ions of both the polarities, resulting in a potential gradient across the region. So absence of mobile charge, presence of immobile impurity ions. This is the important characteristic of depletion region or junction region. The total charge on the impurity ions of one polarity can be found equal to that on the ions of other polarity. Net charge on the ions in the depletion region is 0. Another important property pertaining to depletion region. Here is shown diagrams which illustrate PN junction diode. Anode, cathode, P region, N region. This is the interface, or one can consider it as junction region. Junction region is so thin that we can denote it by a straight line. This is the symbol: anode, cathode, an arrow, and obstruction. Here is shown minority carrier concentration for the case Na very large compared to Nd. Impurity concentration on P side is large compared to impurity concentration on N side. For this case, minority carrier concentration is shown here. In case of P side, electrons are minority carriers. You see, minority carrier. This is minority carrier concentration. On N side, holes are minority carriers. This is minority carrier concentration. When compared to N side, minority carrier concentration on P side is very low. P side, N side, minority carrier concentration is high. That is C. Come to D. Here, built-in potential is shown. P side it is 0, N side it is B. In E is shown charge density. In F also, charge density. What is the difference between E and F? E refers to step-graded junction. Charge density is uniform. You see here, uniform, both sides. In F is shown linearly graded junction. Charge density is increasing linearly like this. With this, we come to an end to the first part on junction diodes. Before closing down, let us recollect the important areas. A general introduction comprising of all salient features of the diode are given: structural features, impurity concentrations, junction formation, impurity addition, dimensions, etc. All are touched upon. Hope this session is useful to you. We meet again in another session on part 2 over junction diodes soon.